Hello, my name is Kala Govindrajan and I'm a senior data cloud architect at Snowflake. Today, I'll guide you through a solution for detecting and predicting anomalies in mission flow sensor data ingested into Snowflake. We'll explore how to train a deep learning model and log it into a Snowflake model registry. And along the way, we will leverage advanced AI capabilities from Snowflake, including Cortex search and leading LLMs available via Cortex. And we will build a LLM-powered chatbot application and Streamlit. By the end of this video, you will have a clear understanding how we process data, how we train models, and visualize predictions using a friendly Streamlit app. So let's get started. So imagine a busy factory floor where multiple machines operate continuously to meet production demands. And these machines are equipped with sensors that monitor critical metrics like temperature, vibration, motor RPM, and motor amps. The sheer volume of the sensor data generated every second creates an opportunity for predictive maintenance and quality control. So the challenge lies in detecting deviations in these metrics. Uh, Patterns that deviate from a normal behavior could indicate potential equipment failures or quality issues. A robust system to monitor and analyze sensor data in real time is essential to preemptively address problems and ensure seamless operations. This solution leverages the power of Snowflake's advanced ML capabilities and LLM features as well to build an anomaly detection system and build an LLM powered chatbot as well. So, by detecting anomalies, the system ensures timely maintenance, minimizes downtime, and upholds product quality. So, in this demo, we'll explore how to train a anomaly detection model using Snowflake and notebooks on the container runtime for ML. So, this powerful runtime delivers a thrice to seven times performance boost compared to traditional open source libraries operating outside Snowflake's infrastructure. Let's dive in and break into the key stages. The key benefits of leveraging a Snowflake container runtime for ML is the performance and scalability that is available. And it's also a fully managed environment. For example, if I want to leverage Keras or and install TensorFlow, I can just do a pip install directly inside this container runtime notebook. Also, I have enabled external access so that I can go out to the outside world and get access to the libraries that I need, and I'm using a compute pool of the size that I need for my workload. So after we have installed TensorFlow, we will be moving on and carrying the library imports. Here we are importing essential libraries like Snowpark, Pandas, TensorFlow, and Keras. These would be helpful to handle and pre-process the data, sensor data that is stored in Snowflake tables. The TensorFlow and the Keras libraries are used to train the anomaly detection model. So by leveraging this Snowflake notebook, we ensure a streamlined data preparation pipeline directly integrated with Snowflake. Next, what we do is we will fetch the data. So the data that actually we are going to create a simulated environment. So what we'll do is we'll create the data set, a simulated data set with different variables like factory floors, so production units, when this which shift this particular this mission was running, what was the mission status, and we are having four sensor variables in this context that is of interest. So we are going to monitor or detect if there are any anomalies in the readings that's produced by these four sensors, which are nothing but the temperature, vibration, motor RPM, and motor amps. In this particular demo, we are doing a univariate detection. Be in the lookout for a multivariate detection demo that's coming out very soon. So once I have the data simulated, I'm storing it in a table called sensor prepared. Uh, this table contains all this data, and I can now look at the sample data set that's fetched from the Snowpark data frame. I am representing the dimensionality here, and also I have 1,000 data points and 10 features, and these are the basic statistics of the data set. I want to understand what are the unique columns present, and I'm setting up the index here. I'm understanding what is the maximum timestamp in my simulated data set, what is the minimum timestamp. Now, in order to split the data into training and test data set and ensuring time continuity, I'm choosing an approach that is very crucial where I'm capturing the temporal nature of the anomalies. So before setting up the model, I'm doing a simple split where we train on the first part of the data set, which shows or simulates normal working conditions. So until this period of time, the machine was seen to work normally, and after this period of time, it started showing some quality issues or some breakdown. And so pushing all the normal working conditions into the my training data set, and the test data set itself will contain anomalies. So I'm going to train the deep learning model with the training data set only. Now, once that is done, I can see a quick visualization of how my sensor readings look like. And then I'm going in and doing normalizing the numeric columns using a min-max scaler for the model compatibility itself. Once the data normalization is completed, I'm removing any non-numeric columns, getting ready for doing the actual model training process. Now, if you look at this, there's 800 data points where the mission was running in a normal status, and there is 200 data points where the machine was actually breaking down. So let's give these 800 data points that was working as sensor data points, but the sensors were working fine, and we trained this LSTM model. Now, why LSTM? For anomaly detection and long short-term memory model is very highly effective because it works well on time series data and can identify irregularities in the sensor data over time. So LSTMs are designed to capture temporal dependencies in sequential data, like time series, and it is crucial for understanding the sensor metrics, patterns based on time. So TensorFlow and Keras provide a robust and flexible API for building these LSTM models, and we are leveraging these workflows, frameworks, and within the Snowflake ecosystem, and especially within this container runtime notebook, and we are avoiding any external dependencies as such. So once we have defining and training the model, what we see is we define the LSTM model with layers for input and dropout, and then dense connections as well. Now, once this is compiled, the model is compiled using appropriate loss function and an optimizer. What we will do is we are starting with the training. We have also defined the epochs and the batch size. Here, this can change according to one's need, and it's more of a trial and finding out what is the best numbers for this. And then I'm fitting the model with all these parameters, and then I'm doing the actual model training. So I'm also saying that store this trained model in this path, the TMP path, in my container runtime itself. Once the training, I can invoke the training. Now this is just a temporary preparation, but I can actually invoke the train LSTM model function using this here, and you see that it has run for 100 epochs. And I also, when I list and go and check in my template directory, I can see that my LSTM model is present here. Once the model has been trained, what I can use is the model actually uses a MAE loss function. So this is appropriate for reconstruction task because it measures how closely the model's output matches the input. All right. So as you can see here, the model loss goes down as epochs increase. So I know that the model is functioning well after this point of time itself. Now this is a very small data set, and this caught up quickly, but for large data sets, it's going to take some more epochs for the model loss to decrease. Once the model is trained on the normalized data, what we are going to do is our goal is to minimize the reconstruction error, and that is also achieved. Now we want to make sure we understand what is the threshold. So the threshold for the reconstruction error, for that what we will do is, before that we will go and save the model and use the model for trained model from the Snowflake registry. Now, what is Snowflake registry is, let's say you store the models and their metadata in Snowflake. I can use a custom class that can actually help you save models, whether they are available from Snowflake or they are coming in from outside as well. The model registry API allows you to log these models, and as long as they are serializable. Models often require static files like configuration files that contains their model weights information. Once and the model registry can actually, you can write a custom model class like this, so that you can log the model registry using your custom model class. So models can generally expose different multiple inference methods, like predict or predict probability that is present, for example, from scikit-learn. So you can define all the syntax and the information or the details of what the model should expect and what is coming as an output within this model class. custom model class, and then you can use the log method from the Snowflake model registry to go and save the model in the model registry itself. Log method will save the model in Snowflake's model registry with the version, the name, version, and what is my input data looking like, what are my different libraries, dependencies that my model would have inside this, and I can retrieve reference to of this particular model object that I have, model registry object that I have saved using this syntax. And then I can also list and see what are the different models that I have in my model registry. Now I'm using a V1 version of the model, and I'm using the model reference and using the run function with predict function to detect anomalies in this particular new or actually the training data set itself. Now you can see that like in my training data set that they were mostly all running condition, and there wouldn't be, if you look at the MAEs that is returned for each of the sensors, they would be well below the thresholds. So I'm actually naming these MAEs for the 4 sensors, and I want to understand in a collated fashion like is if there is any anomalies. Now training did not have any anomalies or would not ideally shouldn't have any anomalies. So I'm just plotting individually each of the sensor values at their loss distribution, and then collated view of all the sensors here. Once we have explored the training data set, we can move to the test data set and carry the detections on that. Before that, we want to calculate the reconstruction error threshold. So for example, for every sensor, I'm trying to find what is the threshold, what is the maximum loss MAE that happened. And so that I can know that anything that is over this particular maximum MAE, it can be called as an anomaly. That is not normal at all, right? So what I'm doing is I'm calculating the loss MAE for each of that, and then maximum loss MAE, and then I'm taking the data points from my test table, and then running prediction on that. Once that is done, I'm actually going and understanding if they went above the threshold that was defined from my training. So those thresholds are determined, and the anomalies are marked here. So as you can see, this is a scored sample data, how things look like. Now, if you look at the actual anomalies marking, it's done here where I'm saying that in any sensor, wherever there was an anomaly, mark it and give me back a collated view. So in this, the test data was at towards the end. So towards the end, we see anomalies coming in. So if there is anomaly in even in one column, then we are calling it as anomaly overall. And then what I'm doing here is I'm actually plotting this. I have a collated view of the training and test where I'm saying the training was all good, but slowly the machine started throwing issues with each of the sensor, and there was a quality issue, and each of the sensor was having spikes or something. So I am seeing anomalies here, that this has been identified, and finally this is also plotted in a graph like this. So you see that there's some spikes and the anomalies have been detected. These are very subtle anomalies. Like if you look at the points, it would be in the 10 to the power of minus something, but it's very small. Like it's not very, it cannot be viewed with human eyes. So these are subtle anomalies. So once that has been detected, all these detections along with the data points and what is the MAE, whether there was an anomaly or not, has been saved in this table called as sensors AD detected. This brings us to the end of the machine learning training and detection. Now we trained a model, and we used the Snowflake model registry to log the model in it, and this is a well organized model registry that can serve as a central hub and a single source for all the models, their metrics, and their metadata. Now once we have that, we retrieved the model from the registry and detected anomalies or newer data as well. Now, what the icing on the cake here is the how we can embed AI capabilities on this machine data. So when I say embed AI capabilities, what I'm going to do is I'm going to use my data sensors AD detected data points available in this table, and I'm going to let business users or non-technical users or any user who wants to converse, talk to the data, right? Ask questions using a chatbot, LLM-powered chatbot about the data. Like, for example, when was the last anomaly seen? Do you think that something is going to break up, or what is the trend for a particular mission, etc. For that, what we are doing is we are leveraging Cortex search, and we'll be leveraging the leading LLMs from Cortex, Snowflake Cortex, which we'll shortly look in the Streamlit app. In the what is Cortex Search? Cortex Search is a hybrid search engine which combines vector embeddings for semantic similarity with keyword search for lexical matching. So you get both the benefits, and it delivers the state of the art retrieval performance. So you do not need a indexing database, separate vector databases. You do not have to do indexing. You do not have to build RAG pipeline separately for on this particular table. Instead, Cortex Search does that everything for you, and you can just search. You can use this search service, and you can just search through your data. So what I'm doing is I'm picking all the details, like the sensor values, the factory floor, when, what happened, at what place, by, and what was the mission condition at that point of time. I'm picking all the values and creating a search service and having a target lag of 1 hour. So which means every 1 hour, if there is a new batch coming in, this Cortex search service is going to refresh its index and understand, okay, what came in new, and it's going to maintain that seamlessly without you have to do any maintenance at all. So everything is automated. It eliminates the need for a warehouse to come in. You have already listed out the warehouse, and all the queries will be directly routed in for, and there's a reduced latency and enhanced responsiveness because of this. So now you see that you have a Cortex search service built on the data, and now we will switch to the Streamlit app where we can do this. So we can see a cool app, what is happening. So this is my first Streamlit app. This is a multi-page Streamlit app, and I have three pages here. This main page, as you can see, it's provides an interactive and visual overview of the sensor data that we were seeing. So anyone who wants to do some quick analytics, they can come and see, look at this app, and also they can monitor some trends, detect correlations, and analyze the sensor readings over time. And this is very helpful, giving basic analytics. Now, if I want to go one step further and predict if there are any anomalies that's coming in my data that I have ingested in the past hour, or past day, or even past 5 minutes, or near real time use case, what I do is I can do that by taking the trained model. So if you look at if you come to the AI ML Snow site and the models, you can see that I have my trained model here, right? So I can pick that trained model and say that, okay, using this trained model, go and detect if there are anomalies that's starting to occur, right? So if I see that anomalies have started to occur in the recent time, and I need to go in and start looking at what needs to be done. So predictive maintenance is the next chapter here, right? So once I have detected the anomalies, using my trained model from the Snowflake registry, I can also look at a quick visualize the plot. I can also go, like I mentioned, the LLM-powered chatbot is available here, which is actually going to help you ask questions. Now, I'll explain the features of this, but when you ask some questions about it, it's going to give you back some, you can ask it to explain, or you can, have a recurring conversation where you ask using the past context, you ask another follow-up question and ask it to describe. What is happening in the back end is it is leveraging the advanced, state of the art leading large language models that is exposed through Cortex. And you can pick any of these large language models, not just these. There is a complete list available, and you can refer to Snowflake documentation. Very recent models that have been added are like Anthropic have been added, and you can leverage any of them. And what you can say is, hey, I want to use this model to answer this question on my data. So how can this large language model look at my data is through this Cortex search service, right? So we created the search service, if you remember. So I'm leveraging that search service and using this model, and I'm trying to answer this. So I say that, like, use my chat history, keep my messages, remember what I'm talking about, and give me useful information. So you can go on asking questions about your data, and it's going to give you back answers. This is more easier for me, or any non-technical user, or anyone who wants to get a quick insight, right? They can come to this app and ask questions to the data, look at the trends, detect, do near real-time detection, and many more. So the possibilities are endless, and that brings us to the end of this demo. Be in the lookout for further demos coming up. Thank you so much.